All right, everybody, welcome back to Top Comics Pressing. In this video, what I want to do is just go over some basics of light and some of the things that make light to be an incredibly kind of weird phenomena and that make it a little bit hard to understand what exactly happens when we are irradiating our comic book with light of different wavelengths. And so I'm not going to spend a lot of time defining light because many of you are already familiar with it. But what I do want to do is just talk about, kind of a standard household LED light and how that differs from when we talk about light and light bulbs scientifically. So many of us are familiar with an incandescent or LED or some of these other CFL bulbs that have been around for a while, and this is what we use to light our home. And so thankfully, we can have all kinds of different options here. What I want to point out is that most standard household bulbs give you what is called, quote, white light, and that is going to be a combination of all wavelengths of visible light. And when we talk about a household bulb, we're going to talk about its watts. And because all bulbs used to be standard incandescent bulbs with a tungsten filament in them, we used to be able to use that wattage as a surrogate for how bright the bulb was. But it turns out that's not the case anymore because we have a variety of different household bulbs. And these each have their own different efficiency. And so the wattage for a household bulb is going to be the amount of electricity or energy going into the bulb, whereas the looms is going to be a measure of the brightness of the light coming out. And I want to say that it is specifically the brightness because we're not talking about total energy of the light, and there's going to be reasons for that. But all of these bulbs are going to be white light, which is going to be a combination of the entire visible spectrum, and that's why we see it as white light. If you're curious, do yourself a favor and go get some LEDs and replace all the old halogens and incandescents. You can see here that to get the same amount of brightness out of a bulb, that would be 700 looms, you would need a 60-watt standard household bulb, and the LED comes in at less than 25% of that at 13 watts. And so that's over, it's roughly an 80% savings in energy to get the exact same result, the exact same brightness out of the LED. And you might ask why that is. Well, all of that missing energy comes out as heat. And it turns out for a lot of what we do, heat ends up being the ultimate product of that. And that's the case here. So anybody who's touched an old bulb and burnt themselves or grabbed a big, headlamp at the after it's been running for a while, knows that that bulb can get very, very hot. And we're going to see that when I talk a little bit more detail about my exact setup for doing this on comic books. Thinking about that heat and the heat dissipation is going to be a very important aspect of that. All right, but I wanted to throw that out there that when we're talking about household bulbs, we use watts and looms, and not wavelengths and photons. And the reason for that is all these household bulbs are all going to be, quote, white light, and they're kind of simplified here just to make it easy for us to figure out what to put in our socket at home. All right, if we're taking a little bit more advanced look at things, we want to define some parameters of light. And the first one here is going to be a wavelength. Now, throughout this video, again, I'm going to use Wikipedia to try to help explain some of these phenomena. The reason I'm doing that, again, is because Wikipedia is freely available to you all. It's easy to search, and you all can go read more about this all on your own just by looking at the title of the Wikipedia page on here. And so I'm really trying to do that to make it as easy for you all to learn more about this as possible. And for at least these kind of really core scientific fundamentals, the Wikipedia pages are actually pretty good. Sometimes they're a little bit confusing because they have to be accurate for more than one subdiscipline, and we'll see an example of subdiscipline discrepancies here in a second. But for the most part, the Wikipedia pages are going to be almost spot on exactly what you would get at a university level intro to chemistry or physics class. So the wavelength here is going to be the number of crests in the distance between two crests in a wave. And so you can see that here is this kind of upside down tent or triangle, half triangle. It's pronounced lambda, and it's the Greek letter. And so we use that for wavelength. And at least when we're talking about light, we're going to use the speed of light. And so if we go look here, a wavelength is defined mathematically as v, which is velocity over the frequency. And that velocity, when we're talking about light, we are going to replace with the constant c, because the speed of light is about 3 times 10 to the 8 meters per second, which is incredibly fast, but it is a constant. It's just a number. And so when I say a constant, for those of you that are familiar with geometry, you might be familiar with the number pi, and it's 3.14 something, 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 something. It's just a number that we need to convert diameters and circumferences of the circle, and so pi happens to be a constant. In this case, the speed of light is a constant as well. Now, if you get into astrophysics and start talking about black holes, these numbers might change a little bit, but I'm not going to worry about that. I'm going to worry about being centered right here on Earth, unless Galactus shows up, in which case, let me know, and we'll be much more concerned about the cosmos. All right, so the wavelength then is a fundamental property of a wave, and it's simply going to be the distance between the two crests in that wave. And there are, a lot of different ways to think about it, but if we've got a box here with kind of our just single wavelength in there, this now might have a frequency of 1 to go from this side to this side, where the frequency is the number of times it goes up and down in a given space. And so we can kind of exaggerate that here with something that has a lot more wavelengths in it. So that's 1, then 2, then 3, and then 4. So this has 1/4 the wavelength, but that means it has to have 4 times the frequency to go that same distance. And so let's put some letters on here. There we go. So we have 1/4 the lambda, 1/4 the wavelength, because the distance between these crests is shorter than here. But because we're still going to be talking about a light wave, that light wave needs to be able to travel the same distance over the same amount of time, because it has the same speed. So all light, regardless if it's blue light or UV light, has the exact same speed, and that's given by the constant c here. And that means that these two are going to be related to each other by that constant. And so we can always get one, and as you go to a longer wavelength, the frequency must go down then. And if you go to a higher frequency, then the wavelength must go down. And so you can kind of see that in the math. The idea that there are multiple wavelengths in light and white light is an old one, and we can attribute that here to a prism. And so this is probably the world's most famous image of a prism. This is from Pink Floyd's The Dark Side of the Moon album cover. But the idea is white light goes into the prism. That prism then separates those different wavelengths into the rainbow, and that is a very beautiful phenomenon, and thankfully we have that. Now, this is probably nothing that's too earth-shattering to anybody, but what I do want to do now is, if we have that wavelength, and we're talking only about visible light, so here on the Pink Floyd album, we've gone from white visible light to all the different spectra within the visible light, but really light is a much more complicated phenomena than that, because it spans the entirety of what is called the electromagnetic spectrum. And all of these different areas of light are all part of the same electromagnetic spectrum, but usually what most people are familiar with is the very narrow band of light that the human eye perceives that we call visible light. But at the extreme end, at the high frequency end, we have gamma rays. So if you're looking to help Bruce Banner transform here, that would be the area of the spectrum you're the most concerned in. The downside is, in real life, gamma rays are quite destructive, and X-rays get to be quite dangerous as well. And there's reasons for that I won't go into. But these are going to be the highest frequency of our end of the electromagnetic spectrum, and they also happen to therefore be the shortest wavelength. They're very, very short waves. Now, as you go from the high energy side to the low energy side, you go through UV light, then visible light, then IR light, then microwave radiation, and then radio waves. And I use an acronym or moniker for this of God examines urinary vials instead of microwaving a radio. And that's something I came up with when I was in elementary school, and I thought it was hysterical. So God examines urinary vials instead of microwaving a radio. So there you go. And that might help you just remember the sequence of them. But the important thing is, scientifically, the entirety of the electromagnetic spectrum can be used for a lot of different things, and we can use different sections or segments of that light of the electromagnetic spectrum to understand different chemical and physical properties. But to do that, what we have to do is understand the wave-particle duality. And wave-particle duality is probably the fundamentally most confusing thing about light. And the general idea is that we can describe light as waves with wavelengths and frequencies and amplitudes and intensities. That is how tall that wave is. But the other thing that's weird about light is somehow that light gets absorbed by molecules and atoms. And when that absorption happens, there's some molecular transition that occurs based on the energy of that light. And to understand that, we have to kind of attribute a light particle, and we call that a photon. And so the photon then becomes the kind of base unit of energy that's carried by a particular wavelength of light. And so you can think about it as being a wave, or you can think about it as being a cannon of little particles of energy. And both of those are going to be true, and that's what makes it really confusing. And so at least if you're confused, you're in good company, because here's a really nice quote somebody put on Wikipedia from Einstein talking about how completely bizarre it is that light has both this property of a wave and the property of a particle, and that neither of them is sufficient to describe light, and you need both the wave and the particle characteristics of light. The reason I bring that up is because when we start talking about photochemistry, photobleaching, when we start talking about chemical reactions, we need to talk about the photons and the wavelength of energy that is going to lead to that particular photon of energy. And because of that, though, we don't really talk about the energy of a photon in terms of its electron volts. What we do is we talk about it in terms of its wavelength. And so when chemists do that, it's kind of inherently confusing because we've gone from the particle side, that is the photon side, and we're describing the particle side in terms of a wavelength, which, by the way, is not actually how that energy is measured. And if you scroll down here, we can see that the energy of a given photon is going to be equal to h, which is Planck's constant, times the frequency. And again, the frequency is going to be proportional to the wavelength. And so if we have the wavelength, we can then convert it to the frequency, and then we can solve the frequency for the energy. And, like I said before, the difference in subdisciplines make this slightly more confusing. So physicists use F for the frequency, which would be great. But you can read here in chemistry, we use E equals h nu, which is kind of a goofy looking V that is used. It's a Greek letter, so nu is nu. So we've got lambda and nu. There you go. But they're just letters. Planck's constant, much like the speed of light, is just a constant. So it's a very important number, but it's just a number. And so we can therefore determine that the energy of a photon is going to be proportional to the frequency of that light. And again, the frequency of the light is determinable based on the wavelength. And all of this discussion about this energy is completely separate from this discussion about this energy. Because again, this is measuring the energy in to make the bulb turn on, and it's measuring the brightness, which is the amplitude, not necessarily the wavelength. So when we talk about amplitude, if we have our exact same waves here, this is going to be a low amplitude wave, but then we might have a high amplitude wave. And these have the exact same wavelength. So there's our wavelength from crest to crest. And so these are the same wavelength, they're just a higher amplitude, and that amplitude is going to be, proportional to the power, but the power is not related to the energy. And so it's kind of counterintuitive, because you'd think you could, in real life, you can get something to run harder and push faster or generate more energy. But in quantum mechanics, if you take a yellow wavelength and you make it 100 times more intense yellow, you never get blue. There's no way to make that transition. And so that's part of what makes light really bizarre. And it's because when you take that, yellow light and you make it more intense, you're just generating more yellow photons. But there's no way for them ever to go to a blue photon. And so that's part of what makes quantum mechanics and quantum chemistry bizarre, is it's quantized. And so if you, again, increase that energy, you don't really change the ability of a molecule to absorb it. Okay, so what kinds of molecular interactions are we talking about, and which levels of the EM spectrum here are we worrying about? Well, let's just start with one that is pretty standard. So most students going through either AP chemistry or definitely college organic chemistry are introduced to the concept of infrared spectroscopy. Spectroscopy, by the way, is just a field using light and measurements about light to understand something about molecules and chemistry. And in infrared spectroscopy, you're going to irradiate molecules, and those molecules, if they have more than one atom, have bonds in them, and those bonds have a certain vibration because molecules are always moving. They're always rotating, they're always translocating in space, and they tend to be vibrating. And so the true description of molecular motion is very complicated. And thankfully for us, though, we can kind of tease apart little bits of it by using different wavelengths of light. And infrared spectroscopy is going to be a very powerful one that has molecular vibrations as the primary mode. And so if you take a molecule and hit it with IR light, you might be able to excite one kind of vibration and not the other kinds of vibration. And so that is exactly what leads to IR spectroscopy. It's very powerful in organic chemistry because we can use it to determine certain kinds of organic functional groups. And there are tables of those that are presented to sophomore organic students or pre-med students, every semester on college campuses. The other one that is maybe a little bit more germane to our discussion about comic books has to do with ultraviolet and visible spectroscopy. And the UV vis spectrum is kind of scientifically lumped together because UV kind of abuts visible. And while there is a hard transition by definition, some molecules can bridge that gap, and some molecules, don't absorb UV light hardly at all, and others absorb a wide range of UV light. And so all of this has to do with the exact composition of that molecule and the exact quantum mechanics that are at play. But what is cool about UV vis is it's one of probably the most powerful forms of analysis in the chemical community. And the reason for that is we can quantify quite precisely the kinds of absorption that happens within a molecule, and we can use that absorption then to figure out how much of a given sample is, or given material is in a sample. And the most common way we do that is with what's called high pressure liquid chromatography, so HPLC, and typically we couple that to a UV. And so most functioning chemistry labs have an HPLC with the UV attached to it. And that's because it's used for all kinds of, reference standards. All right, so, thinking about that then, are there other frequencies? And sure, if you go to the microwave radiation, then you get rotations. And if you go to the radio frequency, you can end up with a different set of molecular interactions that are a little bit more complicated. But, IR is vibrations, UV vis is going to be atomic orbitals and energy gaps, and then microwave is going to be just rotation, just adding spin to the molecule. And so that's pretty cool. Yep, grabbing the wrong stuff here. Okay, so, this is all going to be good and well, but let's tie it in with some photochemistry here. And so the idea of photochemistry is actually using those photons of light to produce a chemical reaction of some kind. And you can see here that the chemical reaction, can be run in the ultraviolet range, and the ultraviolet definition is about 100 to 400 nanometers. For reasons that I won't go into, realistically, these UV radiations tend to mostly be in the mid 200s. So it's very common to have a UV bulb at 254, at 285, at 320, at 350, etc. And so those are considered high energy. So people that look at 254 recognize that that is a very high energy wavelength relative to that 350 nanometer light. So visible light then is going to be much longer, and it turns out for most organic molecules, the overwhelming majority of organic molecules, they don't absorb visible light at all. So the overwhelming majority really only absorb below about 250. Aromatic compounds, and especially some of the aromatic amino acids that are in proteins, happen to absorb at about 250 to 280. Once you get above 300, it gets to be pretty atypical, and it's certainly very rare above 350 for it to have a small organic molecule absorb light in that range. So that's kind of the distribution. And so because of that, most kind of quote old school organic photochemistry was centered around that 220 to 285 nanometer range. But to understand what photochemistry is doing, we can look at this really nice graph here. And this, while confusing, I think does have a lot of the core basics of what photochemistry is. And so this is going to be our, quote, initial starting point. That's where the molecule wants to sit. In these descriptors of a HOMO and a LUMO is going to be the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And you get here because when you start mixing various atoms together into a molecule, you then have a change in the electronic states, that is the positions and locations and orbitals that the electrons sit in. And the exact description of those molecular orbitals is unique for every single chemical out there. And so that gets kind of hard to predict. It can be done, but it's a little bit more than a back of the envelope calculation. And so as not to worry about the exact details, what we typically do is just talk about a HOMO, which is the highest occupied molecular orbital. That's where the electrons are naturally sitting in the unexcited or in the ground state. So ground state is just kind of the background place where it's, quote, happy. The LUMO then is the lowest unoccupied molecular orbital, and that is going to always be one level up, okay? And when that photon hits a molecule, what it's going to do is, if that photon can be absorbed, and the first thing that can happen is that photon could go right through unabsorbed. And for the photon to be absorbed, it has to have a HOMO-LUMO gap that corresponds to the energy of that photon of light. And so, we can probably describe that as, let's just say you send in 100 different photons, and the molecule only has a couple of HOMO-LUMO gaps, or presumably only one HOMO-LUMO gap, then that's going to be the one that will be absorbed by the light. And so the sending light has to match the receiver that has there. If you want a walkie-talkie example, if you ever played walkie-talkies as a kid, if you're talking on channel 7 and your buddy's walkie-talkie's on channel 12, you're not going to be able to communicate. You both have to be on the same channel, the same frequency, for that communication to happen. And that happens on a molecular level too. Molecules need to be able to absorb that photon by having an energy band gap that matches that transition. And when we're talking about photochemistry, we're talking about electronic excitation. And when we talk about electronic excitation, it is the one electron going from the HOMO up into the LUMO energy. So we got ground state here, and this is now our fearsome excited state. So once that electron is up in the excited state, the most obvious thing for it to do is just to fall down. And when it falls down, it will radiate typically heat, and that's generally how the electron kind of plops back. But sometimes in that excited state, we can actually do productive chemistry, and that then leads to the photochemistry kind of concept. Okay, one of the most important photochemical reactions that are out there is photosynthesis, and we're just going to use this kind of as our gateway into the idea, because I think most of us are familiar with the idea that plants absorb light, and when they absorb light, they can convert that to sugar, and then we get to eat them, which is wonderful. And so, nature has a bunch of different chlorophylls. So the light shines on the leaf. The leaf has pigments in it, and those pigments are called chlorophylls, and the chlorophylls are actually what does the absorbing light. And because of this idea of quantized light, and because you need the energy going in to match that HOMO-LUMO gap, nature has designed chlorophylls specifically to be able to capture multiple wavelengths of light. And this is what you see in the fall when the colors change on different leaves, is that green goes away and you see the other kind of chlorophylls hanging out in the yellows and reds and oranges. And each of these different chlorophylls then is kind of tuned for one particular wavelength, and they try to be as broad as possible. And so nature has some tricks to going from a single point excitation to kind of more of a broad wavy, I shouldn't use wavy because light waves is kind of confusing, but a broad kind of blobby looking diagram. And that's what we see here in the chlorophyll. And so as light hits a plant, chlorophyll B can absorb quite nice here, just below 500, whereas chlorophyll A can absorb all the way out here at 650. And you'll notice that these don't overlap exactly, and nature's doing that on purpose because it wants to try to capture as many wavelengths as possible in the light. Now, at least for the comic books, we have, at least what I suggest is a blue LED, and I'll have a different video on where the history of this particular bulb came from, in my opinion. And, you know, why I think that using this bulb is so special. It's a little bit tangential to this discussion, but I wanted to throw that out there. And at least for me, what I use is a blue LED, and that is specifically centered at 450 nanometers. And so that is solidly in the blue region here of our electromagnetic spectrum. I point this out because one of the biggest misconceptions in the field, and one of the things that's most commonly misstated that I see repeatedly, is people using a blue LED and ascribing that to some kind of UV photo bleaching. I want to point out UV is specifically wavelengths under 400, and at 450 nanometers, the blue LED is solidly in the visible region. And because we now understand a little bit about quantum chemistry, it's important to recognize then that the UV light is a much higher energy. It is a much higher frequency, it is a lower wavelength, and because of that, it is going to lead to different photoexcitations. And most specifically, those photoexcitations, especially at low UV light, are going to be very damaging to most organic molecules. But out here in the blue region, there's very few organic molecules that absorb blue light, hardly at all. Okay, and there's another very special thing about blues, and here I'm going to use Maggie's Science Connection because it's the first web page I found that I kind of really liked it as a way to look at it. But as some of us know, we start with the white light, and we have our Pink Floyd Dark Side of the Moon prism, and that's kind of what this graph is showing here. So if you take green light and you mix it with blue light and you mix it with red light, then the center here in the middle is going to give us the white light that we all see. And that's kind of a nice way to think about it. But if you start putting this through filters, and so here is a red filter, and the important thing about color, which is very counter, is if you see a color, that means the object is absorbing all of the other wavelengths. And so here, if we see red, that means the object is absorbing orange, yellow, blue, green, and purple, and only the red light is going through that filter. The same is true here with blue. So if we have a blue filter, that means the object is absorbing red, orange, yellow, green, indigo, and violet, and it's the blue light that's going through, okay? And that's counter because, again, when you see the blue light, you might think that the object is blue, but the truth is the object absorbed everything but the blue. And this is the best kind of graph I found here. So this is off of the Department of Washington at EDU, so you can see that here, but the graph I wanted to share you was this one, and it's because it is now inverted. So instead of describing the wavelength based on what you quote see, it is now describing the wavelength that, or the color that is absorbing that wavelength. Whoops, I went back here. So if you read the text down here, this shows the color will be perceived when a material absorbs in certain regions of the spectrum. And so if you are irradiating at 450 nanometers, let's say with a blue LED, the color that's being absorbed is orange. And so part of the reason that I think these bulbs are so important and so special for doing our comic book cleaning and whitening is that at that 450 nanometers, we are specifically irradiating oranges, and you can see that there is a little bit of yellow and a little bit of red overlap there. And I think that's why in the comic book stain removal and whitening book, the comment and the observations empirically is if you overdo your treatments with the bulbs, you're going to start destroying oranges, reds, and yellows. But it's not coincidental that that yellowing and oranging in the paper is what's taking the brunt force of that blue LED. And we are specifically, therefore, when using a blue light at 450 nanometers, not a UV bulb, but a blue light, you are specifically irradiating all of the oranges and that discoloring yellow and a little bit of the red. And that's why you're getting a whitening process, because you are removing the yellows, you're removing the oranges, and you're removing very, very little bits of the red selectively while leaving the blues and the greens and the other colors untouched. It's very specific, and again, it has to do with a very intentional relationship between the wavelength and the frequency. And the other thing that's very important about these bulbs is at the 450 nanometer wavelength, the overwhelming majority of organic molecules are not going to see that light. They are going to have the light just go right through them. So as you shine light on something like acetone, it'll go through. If you shine it on most plastics like polyethylene, it'll go through unfiltered. And you know that because you can put plastic on top of that light bulb and see the light come through. Okay, so you can do that experiment all on your own. All right, so hopefully this helps explain some details of quantum physics. If I wanted to summarize again here, I would say that light has wavelengths and properties that are very specific to the frequency and wavelength. We can describe light in those terms, but we have this pesky wave particle duality. That means even though we're using a wavelength, what we're really talking about is photons of energy when we start talking about chemistry. Those photons of energy are going to be directly proportional to the frequency, and because the frequency is related to the wavelength, we can go ahead and interconvert those and basically treat them like the same. Depending on the wavelength and frequency of light, you can have different molecular interactions that happen when a molecule absorbs that. So we can have an electronic promotion, you can have a vibration, and you can have a rotational frequency change in the microwave region. And then importantly, each of those different excitations can lead to a different transition, and that's actually ultimately what promotes our transition in the photochemistry region. And as you irradiate with blue light, you're selectively targeting orange and yellows within our comic books. And so I think that that is a good summary there. As I've said before, this is not intuitive, and the only reason I'm familiar with this is because I took this many times in college, and it's challenging. There's a lot of different things to put together. And so if you have questions on it, please leave a comment in the questions, shoot me an email, find me on Instagram or Facebook and send me a message. The more I can do to help you understand these kind of core scientific details, the better everybody in the community is. And so please go ahead and reach out. Thank you for your attention.